but the key difference, these energy levels in the Bohr model are orbits. These energy levels in the quantum mechanical model correspond to orbitals. And this is a more detailed picture of that. And so the red line is an electron dropping from the third floor to the second floor. Third to second. And the green line is from the fourth floor to the second floor. Again, it could drop to any floor it wants, but it would be in different parts of the spectrum. So one of the successes of the Bohr model was that it could predict that there are going to be ultraviolet lines and infrared lines depending on how big of a jump it was. So for example, if we went from n equals 2 to n equals 1, that would be ultraviolet, and you can calculate what the wavelength of that line would be based on the energy difference here. And so that was a success. And so it did have some successes. It predicted lines in ultraviolet, it predicted lines in infrared, but it had a huge failure. And that huge failure was it couldn't predict anything more complicated than hydrogen. And so once we got to helium, then forget it. The Bohr model couldn't make any predictions. Helium, lithium, etc. And the reason that the Bohr model failed is because of this. Because of this. When we're out to n equals 2, we have these set of orbitals here. In one electron, these set of orbitals are all the same energy. But when we have more than one electron, then they are no longer the same energy. So in other words, the energy depends both on n and its shape. And so, So in both models, the Bohr model and the quantum mechanical model, the energy of the hydrogen atom, the energy depends only on n. The energy level. It does not depend on the shape or L, or the angular momentum. For multi-electron, the energy depends on n, as before. And to a lesser degree, on L. The shape makes a difference. And so the spherical shape is going to have a little lower energy than the dumbbell shape here. This happens for one moment. Why? I don't want to get into the reason why. It just is. And so rather than having 4 orbitals of all the same energy here, now we're going to have this. We're going to have this. We're going to split it into sublevels. We have one sublevel here, one some of them will call it subshell here, and another one here. 2p. So it splits. Well, that splitting is going to make the spectra a lot more complex. There are going to be a lot more lines there that you wouldn't see in the Bohr model. And so with this, the success here is this can predict the spectra of things like helium, et cetera, et cetera. So this works. Well, how do we get those energies? We get those energies from the Schrodinger equation, but we aren't actually going to do any math. We're going to do the math-free version of the Schrodinger equation. So we just want something simple. Well, what's simple is we're going to memorize a little pattern that'll help us generate this chart on the right. And this works for many atoms, but not all. And so if we're going to memorize one pattern, we might as well just memorize this one. There are going to be some exceptions to this. The pattern goes like this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 5s, 5p, 5d. What comes after 5d? 5. Actually, I'm missing one here. I should have 4d and then 4, 5F. And then here I should have 5D, 5F, and what comes after 5F? 5G. This has to do with the L. L equals 0, L equals 1, L equals 2, L equals 3, L equals 4. And depending on what N we are, that'll dictate what L values allow, etc. This table, you can just keep going down. And the pattern in the energies goes like this. It's 1s, this 2s is next, followed by 2p, 3s, 3p. After 3p should be 3d. Look at it, 3s, 3p, 3d, but it doesn't work that way. It goes 3s, and then 3p, and then 4s, and finally 3d, 4p, 5s, etc. And so this will allow us to build this chart. And building this chart up like there, and it's not so clear because it depends on this. When I look at it, does it look like the 4s? It looks like the 4s is higher in energy here, right? But most of the time, the 4s is going to be lower in energy for most of the elements that we're doing. There's going to be some slight variation to this. And so this is the way we build up the table. We start off with the 100, or the 1s, and then there's a big jump to the 2s, and then there's a little jump to the 2p. So the 2p are slightly higher in energy than the 2s. And so the greater the L value, the greater the energy. The greater the N value, the greater the energy here. And then we have 3s, and then a jump to the 3p here, and then a bigger jump to the 3d. So the 3d are going to be up here. 1, 2, 3, 4, 5. 5 3d orbitals like this. But the funny thing is, before we hit the 3d, the 4s pop in here, like this. And then right after the 3d, the 4p are here. After 4p, we expect to hit 4d. So where's the 4d? Well, the 4d are way up there. And so this is what we're going to do with this. We're going to look in terms of shells. A shell is a set of orbitals that have similar energy. And so this is the lone orbital here. And all their orbitals of similar energy. So this is the first shell. The first shell only has one orbital. That's the 1s orbital. Then we look at this. Well, the 2s and the 2p, these are pretty close, but the 3s and 3p, now those are farther. And so we'll call this the second shell here. Second shell. Now the third shell, I'd like to include the 3d, but the 3d are too high in energy. And so the third shell are going to be excluding the 3d. This would be the third shell here. And the fourth shell are going to be like this. The fourth shell are going to go up to the 4p. So this will be the fourth shell. And so what's going to happen is that the 4d are actually in the fifth shell, not in the fourth shell. Because the 4d orbitals are going to have quite high energy. D orbitals are higher in energy than p orbitals, which are higher in energy than s orbitals. And so this is what we want to be able to generate. We want to be able to generate the orbital. Well, this is the orbital energy level diagram. And this is for multi-electron species. In Chem 1A, you have to be able to generate both. For the single electron species, which we did on the board, and the multi-electron species. I want you to focus on the multi-electron species. Because single electron species is only valid for hydrogen. So it's a lot of work just for hydrogen. We're not going to do it. Although it's pretty easy to remember it. But one less thing. And so this is the most important. In this diagram, you should be able to draw all the way up to 4p, all the way up to the fourth shell. Like the fifth shell is okay. Fifth shell is going to, let's see if we have the fifth shell here. Do we have the fifth shell here? No, we don't have the fifth shell here. And so what I'm going to do is, let's do a little search. I need to be a little bit more specific here. I need to call it the atomic orbital energy level diagram. And in fact, I better put atomic in parentheses, so I'll definitely want atomic in there. And you know what? It didn't give me atomic. It gave me a whole bunch of other orbital energy level diagrams here. So let's take a look at the images. This is what we call a molecular orbital energy diagram. I don't want that yet. Later on we'll want it. Oh, here's one. Do you recognize this one? This is the one I just had up. This one's actually from the Chem 1A book, Petrucci. It's a good one. The one in our book isn't a good one. Do you want to see the one from our book?
Yes.
The one from our book is really bad. If you drew this in Chem 1A, you would lose a lot of points, unfortunately. Unfortunately, a lot of people draw this in Chem 1A as is. They don't learn the new Chem 1A chart. They stick with the old Chem 4 chart. They get hammered to the point. This is really bad. Does that look good to you? I can't even make sense of it. It doesn't make sense to me. Oh, well, this is only for the n equals 3 and n equals 4, but what happened to n equals 1 and n equals 2? And then what happened to all the orbitals? So I do not like this. In fact, I wouldn't even bother with this energy level diagram. Instead, I would find something, online, which is bound to be much better. And so let's take a look at some others and critique them. Let's see which ones you might like. So this is pretty good. This is different. This is different. This is different. This is different. Those are called molecular orbital diagrams. This is good, except this is only for hydrogen. And then one other thing screwy about this. What's screwy about this? What's screwy about this is they show one line for the S and one line for the P. How many P's are there? Three P's. Can you tell by looking at this?
No. It wasn't 3 in parentheses.
All right, there's 3 in parentheses. You want to draw 3 in parentheses under each of those and say there's 3 lines supposed to be, and then you just drew 1. So this is like, I'm going to draw 1 and then there should be 3 lines underneath. Well, this is so out of ordinary. This is not conventional at all. There's a certain way of doing things. If you're a spectroscopist, once you get advanced, then maybe, do you see that? What's that? N equals? That's infinity. Hard to see. Okay, let's take a look at some more. Let's see, that's molecular. That's why I try to do atomic. But we'll see all kinds of energy level diagrams like this. Energy level diagrams. All right, maybe this one might be a little bit better than the last one. The things I like about this one is they split it, according to L. Now, all these orbitals have L equal to 0. All these orbitals have L equals 1, L equals 2, L equals 3. So it's kind of nice. This is commonly done because in quantum mechanics, we really want to split it based on L. Because the electron can't drop straight down. The electron has to drop at a diagonal according to L. But it's beyond the scope of this class anyway, so it doesn't matter. But they try to do a better job. Do you see the length of this line? This line represents 1. And look at this line, it's 3 times longer. And so if it's 3 times longer, that must mean we have 3 orbitals there. And then this one is how many times longer? 5 times longer than the first one. And this one is how many times longer? Do you see it? How many times longer is this one? How many orbitals does this have? is 7 times longer. Tell me how long the next one's going to be. So if this is L equals 3, it's 7, and L equals 4 is going to have, did somebody say it? 9. But you know, once we get to L equals 50, or whatever, L equals this, because the numbers get huge, are you going to draw a line that long out here? And then can you just eyeball it and see how long it is? No, so this, I don't like this diagram either. Don't copy this diagram. Copy that. This is good, but I don't like this. Well, I'll talk about the arrows shortly. But you know what I don't like about this? I don't like how they do the energies. Look at the energy gap here between 1s and 2s. And look at the energy gap between 2s and 2p. It looks like it's about the same, doesn't it? It looks like all the energy gaps are the same. Is that accurate? No, because things have to converge up here, so the energy gaps have to be getting smaller and smaller as we go up. And so this is not very good either. How about this one? Oh, this one looks pretty good. I like this. But one thing I don't like about this is, you know, I like all the L's to be the same. Here they just shifted everything over, keeping shifting it over and over. And so pretty soon this is going to become very, very long, you know, rather than going up vertically. And so here, you know, I would have put the 2s directly above the 1s, the 3s directly above that, and the 4s directly above that. So I have everything here in line. But can you see this based on shells? They color code this, which is nice also. But here's the first shell, and clearly that's different than the second shell. But this color coding scheme is a little bit confusing, because take a look. Are the green orbitals the third shell? No. The green orbitals are not the third shell. The third shell only consists of the 3s and the 3p, because the 3d actually belong in the next shell. And so what does this mean, the color coding of the green? The color coding of the green means these are the same N. They're the same energy level. They aren't the same energies, of course, but the same N for the energy level. There are going to be a whole bunch of other yellow ones here. And so what we should have is we should have a line. First shell, second shell, third shell, fourth shell. So this is showing up to the fourth shell. This is what you should be able to draw out. If you drew it like this, I have no complaints. This would be okay. If you drew it like this, it's good. Their diagram's inverted from mine. You know, they're going from, take a look at my diagram compared to their diagram. It doesn't matter, both diagrams work. I don't care which one you use. This is the wrong diagram. This is MO, 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 MO. MO is talked about in Chem 1B, not Chem 4. How does this one look? Actually, I don't like this one. Tell me why I don't like this one. Look at the third shell. What does the third shell look like? Not like that. It looks as if the third shell has 3s, 3p, and 3d, right? No 4s. Yeah. Sometimes that happens, but most of the time, the third shell is going to be 3s, 3p. The 3d actually belong in the next shell. And it looks like the 3p and the 3d have the same energy. Is that possible? No. As L increases, so does the energy. So the 3d have to be higher in energy than the 3p. I don't like this drawing at all. Just at the top. Below that looks great. The 1s looks great, the 2s looks great, the 2p looks great. It's just they screwed up the 3d, the fourth shell. Okay, how about this one? Well, here they're using circles instead. Does this one look okay to you? This one looks good to me. Actually, this one looks pretty good because the first shell is the 1s, the second shell is the 2s and the 2p, third shell 3s, 3p, fourth shell is going to be the 4s, 3d, 4p. And then this breaks into the fifth shell, but it doesn't show the entire fifth shell. The fifth shell is going to be 5s, 4d, etc. Here. 5s, 4d. What comes after 4d? 5p. What comes after 5p? I didn't draw it here, but take a guess what comes after 5p. 6s, etc. So we can figure it out based on that. So there's some examples here. A lot of Do you like this diagram? No, I don't like this diagram at all. Again, look at the energies. This is complete, just why even bother writing an energy scale here? And this is paying no attention to the energy gaps. It's totally ignorant of the energy. They're just kind of pretending to pay attention to energy. This one's okay if you're dealing with what atom? The hydrogen atom only. See? How does this one look? This one looks pretty good, doesn't it? You know, this one I like. In fact, this is the one I had up this morning. But this one, you know, there's a pretty big gap here, as we expect. A small gap here. And here we have the third shell. And then the fourth shell, 4s, 3d, 4p. Fifth shell is not shown. And then they show the orbitals. The L equals 0 is an s orbital, which is spherical. L equals 1 is a p orbital, which is a dumbbell shape. L equals 2 is a d orbital. D orbital is like a 4-leaf clover, or this, you know, with a hula hoop. That looks like a p orbital with a hula hoop. These shapes you don't need to know, although these aren't too difficult. These shapes you should know. Spherical, S, and the dumbbell P. So this is a pretty good diagram. So what you need to do is you need to be able to draw a diagram like this out on a piece of paper. All right, now what we're going to do is we're going to put electrons in here. When we put electrons in here, they can go in any of these. Except, you know, if I put into these higher and higher energy orbitals, we call those excited states of electron. If we want the electrons, we'll normally settle to the lowest state. The lowest state we call the ground state. And so the electrons in the lowest energy states possible will be the ground state. So if we look at the hydrogen atom, yeah, we can excite the electron to the third floor. The electron's not going to stay at the third floor forever. It's going to drop. And eventually, it'll go from the second floor to the first floor. And so if an electron is on the first floor here, then we say the electron's in the 1s orbital, like this. Now, when we put electrons into orbitals, we have to pay attention to a couple of things. One thing we have to pay attention to is the Pauli exclusion principle. The Pauli exclusion principle, we need to bring up one more quantum number. We need to bring up the fourth quantum number. So far we brought up 3 quantum numbers. 3 quantum numbers define the orbital. So for example, if I want to define this orbital, it's a 1, 0, 0. And these, I could call it 2px, 2py, 2pz. That's one option. 2px, 2py, 2pz. Another option is just to use the quantum numbers to differentiate between the 3. So this would be 2, 1, minus 1, 2, 1, 0, 2, 1, 1. This 2s is a 2, 0, 0. When I get to 3d, I can differentiate between these. This would be a 3, what is that? 3, 2, minus 2. The next one would be a 3, 2, minus 1. The next one would be 3, 2, 0, followed by 3, 2, 1, and then 3, 2, 2. So what we're doing is we're going from minus L is equal to 2, minus L to positive L. So minus 2 to positive 2. So it goes minus 2, minus 1, 0, plus 1, plus 2. That gives us 5. All right, so this fourth quantum number is what we call spin. And so the electron acts as a little magnet. And so we could have an electron be spin up, which would be plus 1/2, or minus 1/2. These are the only two possible spin orientations. Two spin orientations are possible. And that's it. So what this means is that the Pauli exclusion principle, are we out of time? Yeah. All right, I'll continue.